Last time we talked about analysis and design in general. This time we're going to talk about a specific type of analysis and design. That's object-oriented analysis and design, probably the most popular form of analysis and design today. Um, we're going to start with a background of object-oriented principles, then we'll talk about object-oriented analysis, and then object-oriented design. The principles involve basically these five buzzwords, these five concepts: objects, messages, classes, inheritance, and polymorphism. If you understand all of that, then you'll understand object-oriented principles, the basis between object-oriented programming, as well as object-oriented analysis and design. The first one is objects. So what is an object? Well, an object is something that you can conceive of. Um, it's a thing. It's something that exists. Either you can think about it, it has properties. Sometimes these objects are physical things and tangible things you can actually touch. Sometimes they're only conceptual things, an event occurring at a particular point in time. If I need to remember information about that, then I can think of that as an object. It's something that remembers information. So objects, very important thing about objects is that they remember information. And when we move on into an object-oriented analysis, that's one clue that can help us determine whether something is an object or not. Does it remember information? Do we need an object in order to remember information? If there's no information to be remembered, then it's likely that you don't have an object. Okay, so objects remember things. They have state. They have information, and they encapsulate the information inside them. Objects. The other property that all objects should have is that they should have behavior. So objects should do things. Right? So objects know things and objects do things. There's synonyms for both the data part and the behavior part. So you can see those on the slide. But sometimes they're called methods, for example, for the behavior instead of operations. Actually, in analysis, we're going to refer to the behavior as operations, and as well as in design. In programming languages, though, sometimes the operations are referred to as methods or member functions, things like that. The other thing about an object is that it does encapsulate the information that it remembers. Okay? And so therefore, the only way to access the information that is hidden inside an object is by using its operations, its behaviors. Okay? So the object does completely encapsulate the information on the inside. You really can't see what is hidden on the inside of an object. The only way you can see is get any information about the data is by invoking the operations on the object. The way that we model the operations being invoked is through what we call messages. Right? So in our object-oriented world, the object is sort of sitting there. It owns some information, encapsulates some information, but it won't do anything on its own. The object is basically in a quiescent state until it receives a message. So we say that we send a message to an object. This message is a request for the object to do something. Usually the thing that we're asking the object to do is related to the information that object holds onto. So we may ask, for example, tell me about the information that you have. Summarize it, perform some operation on it, give me some information about the data that you hold, or perform an operation to update the information. Okay, so in some cases, we're just asking about the information. In other cases, we're asking the object to perform some operation to change the state of itself, to change the state of the object. Now, an object, as I said, is quiescent most of the time, is sitting there waiting for these messages to arrive. When it finally receives a message, the object will do something. It will usually, in our model, it'll return back to the invoker of the sender of the message. It returns back to the sender of the message, and usually replies with some information. And then it goes back to sleep. It goes back to the quiescent state until I'm waiting for another message to arrive. Now, the object may do all of the behavior itself, or More typically, in a larger object-oriented world, the object will delegate to other objects to help it, helper objects. It'll ask for the assistance of some other objects because the object itself doesn't have all the information it may need in order to perform the requested behavior. So it may actually delegate to other objects and collaborate with other objects. Now, these messages in the programming language world look very much like procedure calls, and if you're familiar with a programming language like C or Pascal, they have procedure calls. And a procedure call has a name, the procedure has a name, it has parameters and a result. Well, the messages also, the protocol for the messages looks very similar to a procedure call. But the difference is that a procedure call in a language like C or Pascal is the caller, the sender of the invoker of the procedure knows which procedure it wants to invoke. It knows the actual method that it wants to execute. In object-oriented, the object receives a message. So the requester sends a message to the object. It says, I would like this service provided. But the object itself knows how to perform the operation. It may do it itself. The operation may be provided by a superclass, and we'll talk about a little bit later, or may be delegated to some other object. But the requester, the sender of the message, doesn't really know. So the object that sends the message simply is requesting some service. And so that's the difference between a message and a procedure call. The procedure call in languages like C and Pascal, the sender of the invoker of the procedure knows which procedure he wants executed. It actually, in some languages, knows the address of where the code is. But in object-oriented languages, an object-oriented paradigm, the requester of the service doesn't really know how that service is going to be invoked. It's simply, and he doesn't care really either. The requester of the service, the sender of the message, simply wants some behavior performed, sends that off to an object that can perform it. The object itself then determines how to perform the operation. Now, an object is a thing that remembers information. In a lot of cases, we have many, many, many objects all remembering the same kind of information and all performing the same kind of operations. So rather than model each one of those objects individually, usually what we do is we model classes, what we call classes of objects. Right? So we use this psychological principle of classification. Classification theory is a branch of psychology. It is the way the human brain makes sense of the world around us. We classify things rather than thinking of each individual thing as a separate entity. We abstract out common properties of things and think of things in classes. So in object-oriented, the people that invented object-oriented these object-oriented principles in the first object-oriented language invented the concept of classifying things. Oh, by the way, that's a good question. What was the first object-oriented language? And the answer typically that we typically hear is probably Smalltalk is the most common answer. Well, Smalltalk was a very successful object-oriented language, and it came along very early on. It was originally, the original version of Smalltalk was 1972. Then they re-described it and reinvented it in 1980. That's the standard that we have for Smalltalk even on today. But Smalltalk 80 or Smalltalk 72 wasn't the first object-oriented language. It was the first successful object-oriented language. The first object-oriented language, and the folks that really invented this principle of object-oriented programming, was invented in Oslo, Norway, by some researchers there. The name of the language that they invented was Simula 67. 67 is the date, 1967. It's a long time ago, and they invented a lot of these principles in Simula. Simula, of course, was as you might guess, it was a simulation language. And the things that they were simulating in the real world they realized that there were many instances of the things they wanted to simulate. But what they wanted to do is they wanted to model the properties, the common properties, the abstractions of those things. So they invented this concept of a class. So, for example, if I'm modeling traffic in a city, I might have cars, uh, different kinds of cars, different kinds of, or maybe different kinds of vehicles, and streets and traffic signals. Not very many different classes, but you could have thousands and thousands of instances of cars and traffic signals and streets and things like that. So the class it gives you the ability to abstract out common properties of large numbers of objects. In object-oriented programming languages, the class also has the ability to construct object instances. So you actually talk to the class, you send it a message and say, hey, I want you to create me an object instance of whatever the class is able to create. So actually, when you program in an object-oriented programming language, you actually are describing classes and not objects. So in some sense, it's sort of a misnomer to call what we're doing object-oriented, because really it should be called class-oriented. I think it's a little bit too late to change all of the books and everything, but so it's been called object-oriented, but in fact, what we think of are classes of objects, and what we create in our programming language are classes. The objects really don't exist when I'm programming. The objects don't exist until you start running the program. Now, an object is something that remembers stuff and does stuff, right? Has information encapsulated in it, and it has behaviors, has operations. Well, if you think about it, a class remembers some information. A class, for example, remembers how to construct objects, so it has to remember information about the objects that it creates, and also has behavior. One of the behaviors is the ability to construct objects. So in a sense, a class is a special kind of an object. And actually in programming languages like Smalltalk and Java, C++, there is a special class that you really can't see. It's called class, and it's the class of the objects that are classes are instances of class. But that's wrap your mind around that and go crazy. So classes are special kinds of objects that have the ability to construct objects, and in a programming language, the classes are loaded into static memory. So once you load a class, it stays there in memory forever. Objects, on the other hand, are constructed on demand, and they exist for a certain amount of time until you don't need the object anymore, and the memory can be reclaimed. The memory taken up by that object can be reclaimed, and the object can be destroyed. In some languages, the objects are automatically destroyed when they're not needed anymore, such as the case in Smalltalk and Java. And in other cases, you must actually, you the programmer, must deallocate the object, as you must do in C++. When the inventors of Simula 67 looked at the real world, they noticed that the classes of things that they wanted to simulate could be put into a hierarchical relationship. In other words, you could have a bunch of classes that all shared common properties, common attributes, common behaviors, and they invented something called inheritance. We call them superclasses and subclasses, or generalization, specialization. So we see this a lot of times in the real world, that we have this whole inheritance hierarchy. If you recall from biology class, you have the properties of all living things in a nice hierarchical generalization specialization relationship. What's a phylum, kingdom? Let's see, kingdom, phylum, class, order, family, genus, species. Right, is the order of the names of the various levels of this hierarchy. So things in the real world have these generalization specialization relationships. So to support that in the simulation language that they invented, or in OO that they invented, we do this with inheritance. In UML, the Unified Modeling Language, an inheritance relationship is shown as an arrow from the subclass to the superclass. In this picture, we have two subclasses of the superclass video copy. This is a video rental store application. I think we've looked at this before. There's one way to draw it. The other way, of course, would be to have a separate arrow from each of the subclasses to the superclass. These two diagrams would be equivalent then. Sometimes it's convenient to just have one arrow going up to the superclass, but either way, a cassette, this is like a VHS cassette. I guess they still have those. I saw one the other day. And DVDs both contain programming material, but there are some properties such as the title and the information about the cassette, how many times it's been rented, or the video copy, how many times it's been rented, who it's currently rented to, things like that. That information, it doesn't really depend on whether it's a cassette or a DVD, so we can put that information up in video copy. But there are maybe some information that is specific to a cassette, such as is it rewound or not, right? That doesn't pertain to DVDs, so we can store that information in the subclass. There are a set of operations that pertain to all video copies, regardless of whether they're cassette or DVD, and then there might be behaviors that are owned just by DVDs or cassettes. So we can create a nice superclass, subclass, or generalization specialization relationship like this. The superclass defines the protocol that all the subclasses inherit. So whatever set of attributes and operations I specify in video copy, an instance of cassette and DVD should also be able to perform those operations and store that information. In addition, the subclasses can add new attributes or operations that are not defined by the superclass. The other thing is the subclasses can override operations defined by the superclass. Keep the same signature, but provide different implementations. One thing that the subclasses cannot do is override data. So if there's some information that is specified in the superclass, the subclasses cannot change the meaning of that data, cannot override the data, can't delete it, can't change the data type or anything like that. In an object-oriented language, variables generally contain references to objects. Now, you can have some variables whose data type is like integer, then the variables will contain the actual value. But if the data type of a variable is a class, then that variable will contain a reference to the class. Now, if I have a variable whose data type is video copy, what kind of object instances can that variable point to? Well, it can contain a reference to, obviously, to an object instance of video copy, if we had any. But it also can contain a reference to a cassette object instance or an object instance of DVD. Why? Well, a DVD is a video copy, so an object instance of a DVD is, in fact, an instance of a video copy. So since the variable is of type video copy, it can contain a reference to a video copy, a cassette object, or a DVD object. Now, the set of messages that that variable can send to whatever object points to, in Java at any rate, is defined by the class, the data type of the variable. In this case, it would be all the video copy messages. So if there's some sort of a message that you can send to, say, cassettes, even though that variable is pointing to a cassette object, it would not be able to request those services, would not be able to send that message. It can only send the messages that are defined by the class of the data type of the variable. Now, the ability of the object instance to understand the message and perform the right operation is referred to as polymorphism. Right, so a great example of polymorphism is if I have something that has a steering wheel in it. Right? My car has a steering wheel in it, and I turn the steering wheel to the right. That causes the car to turn right. Right? Now I think about what are some other things that have steering wheels in them? Well, A yacht. Now, I don't have a yacht, but if I had a yacht, I would say that it has a steering wheel. And if I turn the steering wheel to the right, what's going to happen? What should happen? Well, it should turn the yacht to the right. Now, how does that happen? Well, there's a rudder in the back, and there's also sails on this yacht, and it'll move the rudder and move the sails in such a way that it causes the yacht to turn right. If I had an airplane, I don't fly airplanes either, but I've seen people fly them, and they have steering wheels in them. And what happens when you turn the steering wheel to the right in an airplane? Well, there's a rudder in the table, and there's also things on the wings, the control surfaces on the wings that cause the right wing to dip down, and the plane sort of like banks over to the right, turns the airplane to the right. So the automobiles and airplanes and yachts all have this same mechanism. They all have a steering wheel, and they all have the ability to turn right. So I can send the message, turn right, to any of those things. So in fact, they're all kinds of vehicles. So I could say, well, I could put this in UML, I could represent this relationship between automobiles and airplanes and yachts to say those are all subclasses of class vehicle, and I can say vehicle has the operation turn right. Now, I can't put the implementation of turn right in the vehicle class because, automobiles, when you turn the steering wheel on an automobile, one thing happens. When you turn the steering wheel on an airplane, something different happens. So I'd actually have to override the operation turn right. Now, if I had a variable of type vehicle, what kind of things could it point to? Well, it could point to an object instance of automobile, it could point to an object instance of an airplane, object instance of a yacht. And if I use that variable to send a message, turn right, to say, and it was pointing to an automobile at the time, then it would invoke the automobile form of turn right. Turn the wheels to the right, move the car to the right. Or if a variable was pointing to an airplane, and I send the message turn right to whatever object that variable is pointing to, then the object would be sent to the airplane and would perform the airplane version of turn right. This is referred to as polymorphism, or from the Greek means many forms. So the things that can turn right take on many different forms.